So exercise number 2 refers to or is similar to a model which you hopefully should have seen in the lecture, but there will be some kind of slight adjustment or slight extension of the model. So consider a legislature consisting of n legislators indexed by one, so indexed by I, and going from 1 to n. Assume n is odd and n is larger than or equal to 3, and suppose that the legislature operates by majority rule. Suppose that the legislators are choosing the amount to be spent on district-specific transfers. Thus, a policy is a vector P1 to Pn, where Pi is the transfer to legislator I's district. There is no predetermined budget, so this is the first adjustment compared to the situation that you had in the lecture. So the set of alternative policies is equal to the n-dimensional space, like the space of, or the n-dimensional space of real numbers, so weakly positive real numbers, denoted by capital P here. Assume that transfers are funded by uniform tax on all districts, capital T equal to, the sum of all the spendings divided by, or the sum of all transfers divided by n, so the amount of legislators. Moreover, because of distortions and tax collection costs, the per district cost of this tax is C of t, where C prime, so the derivative of the cost function is larger than 1. It's strictly convex, so it's this condition here. And if we increase the um, the level of spending more and more, then the marginal costs are going to infinity. The utility function of a legislator I is given by the level of his spending, so the level of the transfer that he's receiving, minus the costs of the uniform tax, which will be imposed on him. Apply the legislative bargaining model discussed in class to make predictions or make a prediction of what will happen in this situation. Okay, so the two adjustments here, or basically they're related. So the adjustment here which is made is that there is no fixed budget, which will be distributed among the districts, but there will be kind of a cost function which is strictly convex, and as a consequence, there will be an interior solution in this game. But yeah, this is what we will see when we start analyzing the game. So the procedure to solve this extension or adjustment with the cost function is actually quite similar to what you have seen in class. So we start by considering any stage t. Okay, so consider any stage t. Y will denote, sorry, I have to make another statement. So consider any stage t where legislator I is chosen. To make a proposal. By Y, we denote transfer to himself. So transfer of, or transfer to himself. By X, we denote the transfer to legislators. in his minimum winning coalition, which consists, consisting of n minus 1 divided by 2 randomly selected legislators. Okay, so this is quite similar to how the model in the lecture, which was presented in the lecture, would be solved. So if you take those n minus 1 randomly selected legislatures, which are part of the minimum winning coalition, and you add the vote of the person who's proposing, you get the simple majority. Yeah, so because n is odd, n minus 1 divided by 2 is basically an even number, which is yet half of all the other legislators if you take out the legislator who's making the proposal. And then if you add the proposal, so one vote, to the minimum winning coalition, it means that if everybody in this coalition is saying yes, then the proposal will be accepted, independent of what everybody else is saying. Yeah, so this is everything that we need in terms of notation. Now, if the legislator I, who's making the proposal in any period t, is making this proposal, so he's giving himself y, and he's giving everybody in the minimum winning coalition, which basically I will here, I forgot to mention this, if I am referring to it, I will shortcut this with MWC. So if legislator I is making the proposal and it will be accepted, his utility is given by the following. So it's delta by the power of t, because there is discounting. It's actually t minus 1. I think in the exercise solutions I made a mistake there. Yeah, I think I wrote delta by the power of t, but it should be actually delta by the power of t minus 1, if I'm not mistaken. No, sorry, it's delta by the power of t. Actually, it doesn't matter at all because it will cancel out anyway, at least the exponent. So it's delta by the power of t times, so now we simply plug in for the utility function. So what he's getting is y, and then he also has costs, which is then c applied on the following. So it's a uniform tax on the sum, or it's kind of it's a uniform tax among all the legislatures, independent of whether they are in the winning coalition or not, and it will be kind of uniformly distributed across all of them. So we divide by n the total amount of spendings, which is then y. So this is the spending to I himself, plus, or the transfer, not the spending. So this is the transfer to candidate I himself, legislator I. And to this we add n minus 1 divided by 2 times x. Yeah, so this is the transfer to all the sum of transfers to all the legislators in the minimum winning coalition. And basically now this is the cost for legislator I who's making the proposal, and in total this term here is the utility of the legislator. If he makes a proposal where he's getting y and everybody in his minimum winning coalition is getting x. Now, yeah, just to 1 second, sorry. So I didn't write anything here. So this is the utility of proposer I. Now, the utility of a member of the minimum winning coalition if proposal gets accepted is the following. So consider any member of the minimum winning coalition, so a legislator who's getting a transfer of X. He is accepting the proposal, so do all the other members of the minimum winning coalition. Then his utility is given by delta by the power of t times x minus the costs, which are the same as the costs for the proposer. So it's 1 divided by n times y plus n minus 1 divided by 2 times x. Now this is the utility if the proposal is accepted. So basically, you can think of the situation as him being pivotal. Yes, so what is his utility if he is pivotal and he's accepting the proposal? So basically, if everybody else in the minimum winning coalition has accepted the proposal of legislator I, and now this one legislator can decide whether to accept or not. So he's pivotal. Then if you would say yes, so he would accept it, this would be his utility. And if he wouldn't accept it, then, so if he does not accept, the game enters period t plus 1. Where his utility is then given by the following. And here you have to consider that we're considering symmetric strategies. So if the game enters the next period, it means that there will be again somebody choosing to make a proposal, and then depending on whether it is actually the legislator who was pivotal in the stage before and decided to say no, depending on whether this legislator will be the proposer, he will be part of the minimum winning coalition, or he will not be part of the minimum winning coalition. The minimum winning coalition. His utility will change, but there is a symmetry in that the proposals done by the person who is the legislator, kind of who was chosen, will be always the same. Yeah. So as a consequence, due to the symmetry, his utility is then delta by the power of t plus 1 times the following. So with probability 1 divided by n, he will be, so in a period t plus 1. So this is analyzed basically from a situation of one stage before this. So this is analyzed from period t and not from t plus 1. So with probability 1 divided by n, the legislator will be the one who actually can make a proposal. And in this case, due to symmetry, he will make the same proposal as the legislator who did the proposal in period t. So then it's simply y minus c 1 divided by n times y plus n minus 1 divided by 2 times x. Then with probability n minus 1 divided by 2 times n, he will actually be part of so he will not be the proposer, but he will be part of the minimum winning coalition. And if this is the case, then he's getting the same utility that he would have gotten if he would have accepted the proposal in period t. So it's x minus c1 divided by n times y plus n minus 1 divided by 2 times x. And finally, he could not be part of the minimum winning coalition, so n minus 1 divided by 2 times n. That's also the probability. So it's actually a plus here. So this is the third case. And then what he will get is he will simply have to pay for the transfers conducted to all members of the minimum winning coalition. So then he only has costs and he does not have any benefit. Okay, so this is the expected utility from period T perspective of a legislator who is pivotal and rejecting the proposal which was conducted by the legislator, another legislator in period T. Yeah, so this is his utility if he doesn't accept it. Now, given all this information, we can write the optimization problem for legislator I in period T, who is deciding on his own transfer Y and the transfers to all his legislators. So the optimization problem of I in T is now the following. So he's maximizing with respect to the transfer to himself. What is he maximizing? He's maximizing his utility. So delta t y minus c of 1 divided by n times y plus n minus 1 divided by 2 times x. This is what he's maximizing, and he's maximizing this under a constraint, and the constraint is basically to make sure that every legislator who is randomly selected into his minimum winning coalition is indifferent between accepting and rejecting his proposal. So basically, this would say that if he finds a level of spending X or transfer X to all the legislators in his minimum winning coalition such that they're indifferent, he can simply marginally increase the transfer to them such that everybody accepts his proposal. And as a consequence, he can make sure with this constraint that his proposal is indeed accepted and the game ends in period T. And the condition here is simply that, just 1 second, you copy this one here. So the utility of a member of the minimum winning coalition if he's pivotal and he's going to accept the proposal made by I is equal to his expected utility if he would reject the proposal and the game would enter the next period. So this is the optimization problem of the legislator who was selected to make a proposal in period T. Now what we can do is we can rewrite the constraint here on the right, so the constraint here in a much simpler way by solving for the cost function. So let me just do this. So the simple let's say simplification of the optimization problem so then it's simply so max over y delta by the power of t y minus, so there's no change here with respect to the original objective function, so 1 divided by n, y plus n minus 1 divided by 2 times x, such that now if you solve the constraint, so the equation there for the cost function, what you get is c of 1 divided by n times y plus n minus 1 divided by 2 times x is equal to 2 times n times x plus delta times x minus delta times n times x minus 2 times delta times y divided by 2 times n times 1 minus delta. Okay, so this is a much more nice looking constraint than what we had before. And now to consider the first order condition. So the first order condition, so we're taking the derivative of the objective function here with respect to y. It's giving us the following, so it's delta t times 1 minus 1 divided by n times c prime of 1 divided by n times y plus n minus 1 divided by 2 times x. This is supposed to be equal to 0. And here you can hopefully see where kind of the assumptions which were made with respect to the cost function in the exercise description are coming into play. So if you look at the first order condition, so the delta t here will cancel out anyway, so it doesn't matter. What you will have is that 1 is basically equal to this here in the optimum. And in order for this thing to be possible, actually this term here must be strictly larger than 1, because if it wouldn't be strictly larger than 1, so if it couldn't be strictly larger than 1 under some circumstance, then since this thing here is smaller than 1, a consequence is that, so if this here would be smaller than 1, then the consequence is that the right-hand side could never be equal to 1, and as a consequence, what must hold is that this term here is strictly larger than 1. Oops, sorry, other way around. Strictly larger than 1, such that there indeed exists a y which is making sure that we have a interior solution. And the the assumption that the cost function is strictly convex is making sure that this solution is indeed the maximum. Yeah, so that the objective function is actually concave. So if you have a strictly convex cost function in this example, the objective function of the legislator who is making the proposal in T will be strictly concave in the transfer to himself. Okay, so let me just make everything a little bit smaller. So now we will simplify the first order condition in 2 ways, which will be helpful. So the first form in which we bring the first order condition is the following. So 1 divided by n times y plus n minus 1 divided by 2 times x. This is supposed to be equal to c prime minus 1 of n. And we can kind of get, or we can use the inverse of the cost function, so the inverse of the marginal cost function, because the cost function is strictly convex, which means that it's a so the slope of the cost function, so the marginal cost function itself, is also a strictly increasing function, and a strictly increasing function always has a unique inverse. Yeah, so this is the reason why you can here simply kind of invert C prime, and be sure that it's actually a singleton what we get as a solution. Good. So this is the first form in which I wanted to bring the first order condition, and you will see why in a second. Then we can further simplify this and get the following: y is equal, so we solve it for y at the end, so y is equal to n times c prime minus 1 of n minus n minus 1 divided by 2 times x. Okay, so basically we will use those two expressions to simplify the constraint. Now, let me give the two expressions here some kind of notations. So this is equation number 1 and this is equation number 2 here. Because now we know for each x, we know how y is looking, so how y should be looking in the optimum. And now we will plug basically the two kind of some of the expressions in equations 1 and 2, we will plug them into the constraint to get a solution for the transfer to all the legislators in the minimum winning coalition. So what we will do is we will plug in c prime minus 1 of n for 1 divided by n times y plus n minus 1 divided by 2 times x in the constraint. So basically here, and we will plug in n times c prime minus 1 of n minus n minus 1 divided by 2 times x for y in the constraint. So basically here. And if you do that, what you get is the left-hand side is then simply c of c prime minus 1 of n. So it's constant. It doesn't depend anymore on x and y. And this is equal to 2 nx plus delta x minus delta nx plus n minus 1 delta x. Yeah, now I just plugged in for y and simplified some of the stuff there. Minus 2 delta n c prime minus 1 of n divided by 2 n 1 minus delta. And now if you solve this for x, what you get is x star is equal to 1 minus delta. So some of the stuff will cancel out. So basically this delta x here, delta nx here will cancel out. But this term here, and then if you solve for x, you get the optimal amount of transfers to all the other members of the minimum winning coalition, but the proposer. So it's 1 minus delta times c of c prime minus 1 of n plus delta times c prime minus 1 of n. Okay, so this is now x star, so the transfer to all the legislators in the minimum winning coalition, but the proposer, depending only on the primitives of the model, so only parameters, so there are no endogenous variables anymore. So it depends on delta, it depends on the shape of the cost function, and it depends on the amount of legislators in the model. Now, if you plug in x star back into equation number 2, then you get the following. So plug in x star for x in equation number 2. And what we get then is the optimal transfer of the legislator to himself, so y star, and this is equal to n times c prime minus 1 of n minus n minus 1 divided by 2 times 1 minus delta. So now it's simply the transfer to the other legislators in the minimum willing coalition. So then c prime minus 1 of n plus delta times c prime minus 1 of n. Yeah, and this finishes this the optimization problem, because now what we have is the transfer to all the other legislators in the minimum willing coalition such that they are indifferent between accepting and rejecting the proposal. So if you pay them slightly more than this x star, so a marginal unit more, they will still they would accept the proposal instead of rejecting it. And as a consequence, then this is what the proposer will be getting, and it will be as usual, also as in the case where you had a budget instead of a cost function, so the model that you saw in the lecture. So the proposer will always get more. So this can be shown here as well. So he always gets more than the other members of the minimum willing coalition. And in addition, what you will also have is that the proposal will be done in the first period. So the first legislator who is chosen to make a proposal will make this proposal, and it will be accepted in the first period. So there is no delay happening in this model as well. And yes, this finishes this week's problem set. And next week, I think that we will have a mock exam which I will solve. Yeah, so see you next week then.